Hello, everyone. Welcome to the 2023 holiday message from the Mindscape podcast. I'm your host, Sean Carroll. Every year we do this holiday message because basically I take roughly 2 weeks off for holiday time. So next week really will take off. There will be no Mindscape podcast released on Christmas Day itself. But the previous week we do the holiday message, which is supposed to be a shorter than usual anyway, little solo podcast, not quite a full-blown podcast, not something that deserves to be a solo episode all by itself, but a little brief reflection on something interesting that is either on my mind at the moment or happened during the year, or many things happened during the year, or whatever it happens to be. So this year, I thought that there was something interesting that I participated in this year. Back in September, I was a speaker at a workshop at the Santa Fe Institute devoted to the topic of immortality. Yes, you heard that correctly. Immortality, living forever. This was the topic. And I love this fact about the Santa Fe Institute, that they're willing to be that adventurous, I guess maybe is the word, to try something different, extraordinarily interdisciplinary. So this is an idea that was actually hatched by David Krakauer, previous Mindscape guest, and Caitlin McShay, who is also at SFI. And they brought together a bunch of people, scientists, but also literary artist type people, people from a variety of different humanities, as well as social sciences and physical sciences backgrounds. And just said, yeah, immortality. Let's talk about it. What does it mean? What are the prospects? Would it be good or bad, etc.? Very specifically, it was not about mortality. Mortality, dying, is something that we don't want to face up to, but okay, we do talk about the prospect of it. And it's very important to, and as I've said several times, I don't think that we do a very good job in our culture right now. But immortality, we don't talk about that much. Probably because it's not very realistic, to be frank. But would it be a good idea if we could do it? How close can we come to doing it? And those were the kinds of things that got talked about at the workshop. So very little of the workshop, actually, in retrospect, was literally about immortality. You know, immortality is one of those words that carries implications of the infinite, living literally forever. Most of the people who rose to the occasion to give talks, including a few previous Mindscape guests like Jeffrey West, talked about longevity of individuals, of ideas, of cities, and so forth. My job was to bring the cosmic perspective here and to kind of be a downer, to say that even in principle, as far as we understand the universe right now, true immortality is really not quite possible. Maybe the universe can be eternal and infinite, but what we think of as human mortality can't. So, but it was a wonderful workshop overall. It was very stimulating, people coming from completely different angles on this question, really thinking it through, even though it sounds a little silly at first glance. It's important to face up to what one of my old philosophy professors called limit concepts. You know, push yourself to the limit of what you're comfortable thinking about or contemplating, and look at what you learn, look at what you bring back. What does this tell you about yourself and your more realistic concerns here in the world? So that's what we're going to do here in this particular holiday message. So let's go. The first question to confront when you're told to think about immortality is, what does that mean? What is the definition of immortality? And you might say, I know what that is. It's easy. It's living forever. That's what it means to be immortal. But okay, what do you mean by living? In other words, some people at the workshop raised the issue that if the universe is eternal and you have some version, and we have to be careful about what we mean by some version, of Laplace's demon going on, then in some sense you'll live forever. If there's a famous example that physicists always use when they talk about the black hole information loss paradox, right? They say, look, if you have a book and you throw it into a fire and the book burns, then the information that was in the book is lost in practice to you. You don't know what the book says anymore. But in principle, if all the laws of physics are being obeyed, then the specific ways in which the book burned are implicated in the specific kind of heat and light and ashes that were produced by that fire. So if you had infinite capacity to figure out what all that information was and also to reconstruct it, etc., you could read what was in the book. This is, of course, exactly what Laplace's demon would have to do. The hypothetical vast intelligence proposed by Pierre-Simon Laplace that could know the position and velocity of every particle in a classical universe and use that to completely know both the past and the future. There's some complications here depending on your favorite version of quantum mechanics, etc., but the point remains that in some sense, modern physics thinks that the information contained in you persists through time. This doesn't count as immortality. That is my first message. We talked about this. I think most people actually agree with me on this one, but trying to get exactly straight what it does mean. So, what does it mean to say that you have died? I mean, the information that is in your brain, etc., is still contained in the universe. So what exactly happens? And if you really dig into it, I would definitely be someone who argued that you at this moment is not exactly the same person as you 5 minutes ago, much less 5 years ago. We change over time. So if on the one hand, we're always changing over time, inevitably, and on the other hand, the information contained within us, in principle, persists out there in the universe, then either we live for just a moment or for forever, right? Of course, the reconciliation to all this silliness is to admit that we are talking about the macroscopic world. We're talking about an emergent level of reality when we talk about people and their lives and deaths. So, in fact, what happens is, forgetting about Laplace's demon and microscopic information, various parts of the universe come together to give rise to you, a person, and we call that being born or being conceived or whatever moment you want to attach to the first moment when you were really being you, and then you live your life. And over the course of living your life, there is accessible information about you. By accessible, I mean we're not being Laplace's demon. We're not pretending to know where every single molecule in your body is, but maybe I can know roughly where you're located, how tall you are, what your hair color is. I can talk to you about your wants and needs and things like that. That's the accessible information that defines who you are as a macroscopic person. And over the course of your lifetime, that accessible information comes and goes. And then once you reach death, at least in the current way that it's understood at our current moment of technological progress, that information about who you were, your hopes and dreams, etc., is no longer accessible from you, right? It's no longer accessible from your body. Maybe you wrote it down in a diary or something, but we don't count that as you. We don't count that as being immortal. So I think that as long as we understand this sort of macroscopic emergent perspective, it makes sense to say that real human beings have some kind of finite lifespan. I think it's also very important here to imagine that these real human beings we're talking about have a kind of finite memory, right? Like there's some psychological continuity. It is not absolute. We do not remember everything that happened to us, but it is not absent either. If we did remember nothing about what happened to us from moment to moment in time, then this notion of individual identity and psychological continuity over time wouldn't be that useful, right? So I think that as long as we have this macroscopic perspective and we admit that even though we change over time, we don't change utterly over time. We keep some information, some memory, some common characteristics of who we are from moment to moment. I think it's perfectly well defined to say that people have a lifespan, and as far as we know, that lifespan is not infinite. Now, some of you will know there is a possible loophole here in the case of the many worlds interpretation of quantum mechanics, right? Famously, there's this idea of quantum immortality. Max Tegmark, another previous guest, and others have talked about quantum immortality. And there's different ways to play this game, but roughly speaking, the idea is that you are this collection of atoms and other excitations of elementary fields that make up the universe. You obey the rules of quantum mechanics, let's say, and let's say that we believe in the many worlds interpretation of quantum mechanics, then different things happen to us. So on different branches, we might act in slightly different ways. We might respond to other kinds of branching events where quantum measurements are made, Geiger counters, universe splitter apps on our iPhones, or what have you. So we are slightly different people descended from us on all these different branches of the wave function. And either you can play this game different ways, like I said, but you can either bring this about by some quantum random number generator hooked up to a device that will kill you, or just by letting time evolve and seeing what happens. One way or the other, you can argue that there will always be one branch of the wave function on which you remain alive indefinitely long. Even if in the overwhelming majority of branches of the wave functions you will die, there might be one branch in which you live forever, essentially. Now, I don't think that this is a very illuminating thought experiment, personally. I think that the technical parts of it are all plausibly correct as far as we know. We don't specifically know how many branches of the wave function there are. If there's a finite number, that changes things from an infinite number and so forth. But let's grant all of the assumptions of the thought experiment and imagine that somewhere out there in the many branches of the wave function of the universe, you do live forever. There is some kind of quantum immortality. Then longtime listeners will know that I'm going to say I don't care about that, mostly for the reason that if you want to believe in many worlds at all, okay, if you want to accept that as the correct theory of the world in which we personally do live, then you have to accept a couple things. One is that not all the worlds count equally, okay? There is an amplitude. There is a wave function squared, which plays the role of how many copies there are, right? That's why you get the Born rule. When you say, I'm going to have a probability, I'm going to predict the outcome of a quantum measurement probabilistically, I'm going to say it's 2/3 for this, 1/3 for that. In many worlds, both outcomes actually come true. So why in the world would you say there's a probability of 2/3 versus 1/3? The answer is that the 2/3 branch counts more in a very quantifiable way. And if you accept that, then these branches on which you live forever count enormously tiny amounts, like infinitesimally, almost immeasurably tiny amounts. It's not something that should affect your everyday life in any way, the prospect of this living forever. And as I've said, before many times, including, by the way, in my new Wondrium course on the many worlds of quantum mechanics, when we think about why it would be bad to die, if you think that way, you're thinking about it now. There is some value right now into thinking that I'm not going to die within the next couple of minutes, okay? So even in a classical universe where there's only one world, there's not many worlds or anything like that, you still want to live a long time, even though once you're dead, you're not going to care about it. The reason to be upset about the prospect of death, which is a perfectly legitimate reaction to have, is not because once you're dead, you will be sad. That was never the idea. The prospect of dying in the future is upsetting to me now. And so the same thing is true with quantum immortality. The idea that there is a branch of the wave function where a version of me will continue forever is completely swamped by the fact that on most branches of the wave function, the overwhelming majority of them, there is no version of me that is continuing forever. So I feel about that in exactly the same way that I would feel about living in a single universe where I had a finite lifespan. And of course, the other thing to keep in mind is that these different versions of you are not all you. They are your descendants in time. You have to update what you mean by personal identity if you're going to accept many worlds. So it's cold comfort to think that there's other people who share a common past with you that are going to live forever, but you're not. So I think that there's no solace to be found in the many worlds interpretation of quantum mechanics if what we want is to live forever. Now, that's a little bit of science I wanted to get out of the way, not because it's really what I care about in this brief podcast, but because people will be thinking about it. Once they hear it's me talking and once they hear immortality in the title, they'll want to hear about the quantum immortality thing. That's my take on it. I want to actually be a little bit more down to earth here. First, let's ask whether or not in the real world, if there was actual immortality, not just quantum immortality, if there was a feasible chance that I could live on a lot of branches of the wave function for effectively forever, what would that be like? And for that matter, would it be good? So there was one person, I'm very sorry I forget who it was. There was a person at the Santa Fe workshop who had the very, very good idea of taking a poll of the people in the room. And remember, the people in the room are selected to be in some way interested in the topic of immortality, one way or the other. I mean, they didn't volunteer. They were asked, and they said, okay, I'll go. So they were chosen as people who might have thoughts about immortality. Let's put it that way. And the poll question was very simple. If you could live for 10,000 years, and let's say that you are as healthy for all those 10,000 years as you ever have been, okay? So you don't just decline in capabilities for all those millennia ahead of you. Would you want to? Would you want to live for 10,000 years? A sizable majority of the room said no. They would not want to live for 10,000 years. That's too long. I was one of the minority there. I absolutely voted to live for 10,000 years. I mean, I am absolutely impressed by the number of things that I want to do in life that I don't have time to do, right? So the idea of 10,000 years to kind of relax and get it all done, that's very, very appealing to me. The specific number, 10,000 years, is very hard to judge. If you think very roughly speaking that we all live for, on average, order of magnitude for 1 century, for 100 years, that's multiplying the average human lifespan by 100. It's very hard to judge whether you would go a little bit crazy. And if you look into literature, which people at the workshop were absolutely interested in doing, it is very interesting how many cautionary tales there are about immortality. There's a story by Jorge Luis Borges, who we talked recently about on the podcast with William Egginton. He wrote a story called The Immortals. There it is. And I'm not going to spoil it for you. It's a short story. You can find it on the internet very easily. But suffice it to say, there are characters in the story who are immortal, and they're not living very enjoyable lives. In fact, they're called troglodytes. It's sort of for various reasons, right? Like you run out of things to be interested in. And even more, you're not in a hurry. Right? If there's some experience you want to have, according to Borges, but you're going to live forever, what's your motivation, really, to get it done anytime soon, right? It'll come around once in a while eventually. So I think that's quite plausible that you would actually feel that way if you were literally going to live forever. My favorite example of this kind of story, which I'm sure I mentioned on the podcast before, but I can't remember when, is Julian Barnes in his book, The History of the World in 10.5 Chapters. The last chapter is called The Dream, and it's a guy dies and he goes to heaven, so he can be immortal. So there's the gimmick in Julian Barnes's version of heaven is you get anything you want and you can live forever, but we're not going to tell you what you want. You have to invent what you want. So I like that version of it because it faces the reality of our finitude, right? Like time is infinite, possibility is infinite, but our imaginations, or maybe to be more fair, our desires or our interests are finite. We human beings are finite. So you're placed in a situation in heaven where you get anything you want. And the particular guy we're looking at here is not the most imaginative person in the world in the context of the Julian Barnes story. It's in a novel, History of the World in 10.5 Chapters, but the novel consists of a series of stories that are more or less unrelated. So basically, he's a middle-class English bloke, and he wants to, have breakfast foods for dinner every day and have sex with a lot of beautiful women and meet all of his favorite celebrities. And then he wants to play golf every day and get holes in one. And if you have enough time and you can do anything you want, then you can do all those things, right? And at some point, given that you are finite, and I think that this is just very, very telling, at some point you run out of things to be interested in. This is a much broader lesson in my mind. We sometimes talk about eternity or infinity or immortality as human beings. We don't really think about it deeply enough. We kind of tend to conflate immortality with longevity, with big numbers with infinite numbers, right? But they're not really the same thing. And we human beings, at least at the moment, at least in the kind of form that human beings are known to have, are finite. And that includes our desires and our hopes and our ability to imagine. So our hero, our protagonist in the Julian Barnes story, eventually asks his guardian angel. He says, like, is there any option to no longer persist, to basically die, right? To stop being here in heaven. And the angel says, yes, that is absolutely an option that you can take. And he says, wow, that's kind of amazing. Has anyone ever taken this option, like to give up on heaven? And the angel says, everyone takes the option. That's what's going to happen, says Julian Barnes. We're not going to want to actually be immortal. And I don't know, though, about 10,000 years. That's the interesting question. How long would you want to live? I completely agree that you would not want to live for infinity years. But I think 10,000 years you might want to live. Finally, of course, on The Good Place, the TV show that was recently quite popular, I encourage everyone to watch The Good Place. It was a great show. And at the end of the show, they came to a similar conclusion. Again, I'm not going to spoil it. I kind of spoiled the Julian Barnes story, but I'll let you watch The Good Place. They had to confront exactly the same kind of question, and they did it in a very interesting way. So I think that, again, there's a difference between living forever and living for 10,000 years. I don't want to live forever, but I personally do want to live for 10,000 years. I'm interested in what Mindscape listeners might think about this. By the way, one of the people who was at the workshop was Ted Chiang, who is a science fiction writer. Excellent writer, wrote a lot of good stories, including ones on which movies were based, like Arrival, for example. I can highly recommend his books. And he's actually spending time now at SFI, hanging out with the Santa Fe people. And he gave a little talk where he made an impassioned plea for why immortality would be bad. But it was communally based. It was not individually based. So it wasn't that you would get bored. It was kind of more along the Borges line. He was saying that society would sort of stagnate. We would fall into a rut. There is something to be said. There is an evolutionary reason why, and not just biological evolution, but social evolution, why people need to die. Because people get stuck. People are very successful in one mode or another, and they're going to keep trying that, and new ideas bubble up from younger people. And if you have immortality or effective immortality in your society, there are no younger people. You got to say, look, sorry, we cannot have kids or anything like that, or we'll just exponentially grow in numbers. That would be bad. So no more kids, no more ideas, no more young people, no more youth with their energy and so forth. There's a footnote here about youthful energy, which I personally think youthful energy is really, really important. And there's a whole political, social kind of commentary to have that I'm not going to go into right now about the weirdness with which certain culture war battles are fought on the grounds of what the kids in the universities and the colleges these days are doing. I think that kids in universities and colleges, they're not kids anymore. They're grown-ups by the time they're in university, but they still have that energy, that drive, that desire to make a difference in the world. Sometimes that's going to lead them to go too far, to be extreme, to go a step beyond where they should go. And by all means, they should be told, don't go there. But we still need to let them make those mistakes. We need to encourage that youthful energy and that willingness to change the world. Okay, that little footnote is now gone. I disagreed with Ted about falling into a rut a little bit. I mean, I think there are ways to, it's kind of a silly argument because we're not going to be immortal or anything like that. I think that there would be ways to keep society interesting and new and novel, even without actual new young people being created. There could still be new ideas that are being created. But I get it. I get the argument, and I think it's very valid. So I think that the point of this little digression, this long digression, is that it's not obvious that immortality is a good thing. We need to sit and think about whether we want it, as well as what I'm going to eventually get to here. The point of this little podcast is, can we possibly get it? But one final thing before we get there is that There's different kinds of immortality, of course, right? Ernest Hemingway famously said that everyone dies twice, when they stop breathing and the last time anyone ever thinks about them or says their name. Sometimes this quote is attributed to Banksy, but Banksy was clearly quoting Hemingway here. You can have a legacy, right? You can physically be dead, but you can live on in the impact that you've had on the world. It reminds me, there was a recent Ask Me Anything question by Mark, with no last name, which asked whether or not I cared how long I will be remembered, right? So there's two different ways in which we're going to die. We're going to die because we literally physically die, and then because everyone forgets us. And I think that, this is one of the many ways that you can emphasize the stark reality of the end of our lives, right? It's not just that you stop existing, but all sorts of things associated with you come to an end. If you like to read books, there is a last book you will read. There is a last time you will see the person you fall in love with. There is a last meal that you will have. There is a last good idea that you will have. And then after you're dead, there's a last time someone thinks about you, a last time someone says your name out loud, a last time someone reads about you in a book or anything like that. These are all implications of the finitude of human life. Of course, Hemingway is trying to say, some people last longer than others. Some people, they're going to keep reading my books, who he was talking to. I'm not sure about that. But my answer for the AMA question was, I don't really care about that. I'm very much about the time that I have where I'm conscious here on Earth, living my life. I'm much less interested in what's going on after I am dead. In fact, there was a wonderful little intervention by Scott Small, who was another person at the workshop. He was a neuroscientist, and he mentioned the idea of a ceremony of forgetting, probably in the context of ceremonies of atonement, forgetting our sins, forgetting the bad things that we've done, but the more general idea of letting things go into the past. And I think this is sympathetic with what Ted Chiang was saying. If you take mortality seriously, if you don't struggle against the inevitable passing of ourselves and our memories, then rather than doing that, let's honor it. Let's say, okay, we remembered you for a long time. We're not going to think about you anymore. We're going to honor your memory by forgetting, by moving on, because life continues for the people who still are still around. I thought that was very touching, probably difficult to pull off in practice. But it does raise the question of what can we do in practice, right? Okay, so we've been talking about whether or not immortality would be good or not, how to think about the implications of it, etc. But it doesn't matter if you can't do it, right? Then we're just sort of wasting our time and telling each other stories. Again, maybe it matters in the sense that I mentioned earlier, that we help ourselves conceptualize the finite life we have, and that's fine. But is it just that kind of thought experiment usefulness, or is there some realistic prospect that we could live forever? By the way, I do like to emphasize that as far as I can tell, the idea of extending our lives much longer than they currently exist is very realistic. Not necessarily within my lifetime, but, this is a biology problem, not a physics problem. There's no problem as far as the laws of physics are concerned with repairing yourself as a biological organism. It's not built into what our biological capacities actually are, but that's okay. We can change them, right? That's what medicine and biology are all about. One of the first podcasts I did, or at least, in the first couple months, was with Colleen Murphy, who is a researcher at Princeton. And I was happy to see she just has a new book out called How We Age. So I strongly encourage you, if you're interested in this life extension question, read what Colleen says. She's not a crazy person. She's actually a very serious scientist. And she will give you both what is plausible and what we cannot do based on actual experiments that have been done. But if you're asking, 1,000 years from now, how long can we extend our lives for? We have no idea. And the answer might very well be effectively forever, as far as I know. I think it's important, given what we were talking about last week with Adam Frank and aliens and so forth. It's important to recognize that if you are contemplating interstellar travel and going, it's not really realistic, it will take thousands of years, maybe our lifespan is tens of thousands of years or millions of years. So maybe that becomes totally realistic. But even that is very different than infinity years. It's not quite immortal, right? So let's actually think, and now I can talk about the science that I tried to bring to the workshop on the cosmology and physics side of things, right? Let's be very, very honest and ask, would it be in principle possible to live forever in some recognizable way? Given that we human beings are biological organisms, as I said on a recent podcast, we are quasi-homeostatic non-equilibrium systems embedded in entropy gradient. And the fact that the entropy of the universe is increasing is crucially important to life, right? Life on Earth in particular is possible because the sun is a hot spot in an otherwise cold sky. That's a reflection of the fact that we are very, very far from thermal equilibrium. We are non-equilibrium processes. If you took all of the information contained in me and you wrote it in a book and then put the book on the shelf, that book would not be me, right? There's nothing happening. There's no time evolution. There's no development. There's no increase in memory or experience or anything like that. To be alive, to be human, to be a living organism in the way that we think about it, it is necessary for time to pass and for you to accumulate memories and experiences and knowledge, as well as making predictions about the future. And that is all very strongly based on the arrow of time. And the arrow of time, as you all know from listening to the podcast, comes about because our universe used to have very low entropy. Entropy thought of as a way of counting how many microstates look a certain way in the macroscopic configuration of the universe. Our early universe was hot, dense, smooth, rapidly expanding. Turns out that's a very, very tiny number of microstates look that way compared to the number of states of the universe that look the way that our universe looks today. And in turn, the number of states that look like the universe today is very, very small compared to how we could look. That is to say, we are continuing to approach thermal equilibrium. The actual thing that is happening is the universe expands from a hot, dense state. It cools off. Gravity pulls things together. We make some black holes. Black holes have huge amounts of entropy. We also make galaxies and planets and stars, as well as life and so forth. And eventually, it all goes away. That's the big lesson that I have for you here. Not necessarily a cheerful one, but all of that churning, interestingness, and complexity in the current universe will eventually disappear. Stars will burn their fuel. It's going to take a long time, okay? So the universe today is, again, order of magnitude 10 to the 10 years old. The last star will probably peter out around 10 to the 15 years from now. So that's plenty of time to do lots of interesting things. But eventually, those stars are going to die. They'll fall into black holes. The black holes will evaporate, and the evaporation products will scatter across the universe. We discovered back in 1998 that our universe is not only expanding, but accelerating. We attribute that to vacuum energy, to the cosmological constant, to the energy of empty space. And there's going to be nothing but empty space left if you go far enough into the future. All the black holes will evaporate into photons and things like that. Those photons will be stretched by the expansion of the universe into essential non-existence for all intents and purposes. That's the high entropy state of the future universe. That's thermal equilibrium. In fact, I'm sure I mentioned this one before also, but one of my favorite papers was with Aidan Chatwin Davis. We wrote a paper that related this particular feature of the universe in the presence of a cosmological constant or a non-zero vacuum energy. The universe empties out and becomes smooth and featureless. We related that to thermal equilibrium, right? To the thermodynamic tendency of entropy to increase in a box of gas until you reach equilibrium, and then it just stays at that constant amount. We wrote a very fun paper that said that you can actually prove what is called the cosmic no-hair theorem. The cosmic no-hair theorem, originally coming from Bob Wald, showed that if you have a universe with a positive cosmological constant that does not recollapse, then eventually it just empties out. You get nothing but empty space. De Sitter space is the technical term. And so that's a result in general relativity. And what Aidan and I did is not use general relativity. So we did not use Einstein's equation of general relativity. Instead, we used a definition of entropy that is applicable to a situation where you have both gravity, so there's entropy in the gravitational field, but also you have matter, you have stuff, you have photons and things like that. So there's both matter entropy and gravitational entropy. This definition was written down by, I was amused to remember, two former Mindscape guests, Raphael Busso and Netta Engelhardt. They collaborated on a paper together. And so they wrote down this definition of entropy that applies in cosmological situations. And what Aidan and I did is to say, okay, if this particular definition of entropy simply rises for a while and asymptotes to a constant finite value, what does that imply about the expansion of the universe? And we proved that it implies that you approach de Sitter space. Just like the cosmic no-hair theorem, you approach an empty universe with exponentially growing expansion, etc. That is the highest entropy state the universe can be in. Empty space, nothing going on. So what that means is, back to reality now, the fact that we're not there, the fact that we're not in empty space, the fact that we are lower entropy than that, allows life to exist. The initial low entropy of the universe is a resource that we are using up. We are increasing the entropy of the universe, approaching that final empty thermal equilibrium state, and we have a finite amount of that resource to use. We need low entropy energy. Technically, you might call it free energy in the technical physics term, but it's not like energy for free. It's energy that is available to do useful things. We use free energy to metabolize, to act, to think, to live, right? That's the usefulness of having the sun there as a hot spot in a cold sky. So we need that in order for life to exist. You see how this is relevant to the question of immortality. Now, as I've often talked about one way of thinking about this universal process is that complexity comes into existence and then evaporates away. There is a simple initial state for the universe. There is a simple final state for the universe. Complexity comes in the middle, and that's where we are right now. So people, when I say that, always want to know, are we exactly at the top of the complexity curve, or are we slightly past it, or before it, or what? And we don't know. I don't know a good way to quantify that. I do have one little piece of information that maybe is relevant that I shared with everyone at Santa Fe. One thing that you can actually calculate is the rate of star formation in the universe. So how many stars, and when I say in the universe, I mean in our observable universe. So the total amount of stuff is finite. We're looking at some co-moving volume with a certain number of atoms inside and asking how many stars are produced. And you can look out there in galaxies and star-forming regions. There's plenty of stars being produced. But then you do it carefully, and you learn that we are past the era of peak star formation in our universe. Star formation peaked around 4 or 5 billion years after the Big Bang, and now we're 14 billion years after the Big Bang. Star formation rates have been declining for almost 10 billion years. So that does not mean that complexity is declining, but it means that the particular kind of complexity definitely is not increasing over time, right? Like all the stars, most of the stars that have ever been formed in the history of our universe that will ever be formed have already been formed. This is a reminder, and I'm not saying this because I want it to be true. This is just what science is telling us. The interesting part of the life of our universe is finite. You can judge what exactly the number is in different ways, but it's not going to last forever. The universe started simple. Complexity comes into existence and flourishes for a while, but that while is finite. We will eventually evaporate, dissolve into the surrounding thermal equilibrium. That is the sad science message that I had to bring to the folks at Santa Fe. We can even quantify this a little bit. Those of you who are physicists out there might know there's a famous paper by Freeman Dyson from back in 1979. Freeman Dyson, famous physicist, wrote a paper called Time Without End, Physics and Biology in an Open Universe. I think this paper is famous anyway. It was clearly not famous enough because no one else at the workshop had heard about it besides me. But what Dyson was saying is that let's imagine, so he's 1979, he's writing this, right? So they didn't know a lot about the future history of the universe. Maybe it will recollapse, maybe it will expand forever and so forth. Certainly the idea of the cosmological constant and eternal acceleration was known in principle, but was not considered a leading candidate. So people didn't pay a lot of attention. So Dyson says, what if the universe is open? That is to say, he's imagining that the total amount of matter in the universe is not enough to cause the universe to stop expanding and then recollapse. So the universe will last forever. So that's the kind of universe in which you might say, well, maybe there's a hope for being immortal, right? The universe lasts forever. But also, it's expanding, again, not thinking about vacuum energy or the cosmological constant, but the temperature is going down, the density of matter is going down. So you might worry that, we run out of energy, run out of stuff. And Dyson's insight, his argument was, you could live forever in an open universe because if you think that it takes a certain amount of energy to have a thought, well, what you can do is just have thoughts that take less and less energy but take more and more time. So basically, Dyson argues there's a competition. If you allow yourself to count as a thought, a certain amount of energy expended, but you give yourself more and more time for it to happen, what is the sum that you do? Do you get to fit an infinite number of thoughts into the universe, into this infinitely old universe? And he says the answer is yes. The universe is getting less and less dense, colder and colder and colder, but you can still fit an infinite number of thoughts into it. Very interesting. And you might think at first that adding a cosmological constant to this question doesn't change it very much. It's still an open universe. It's still cooling off, but not that much differently than it would an ordinary open universe. But there is a physics difference that actually matters because, as I said, the state that we approach is not Minkowski space, which would be empty space with nothing in it at all, but it is de Sitter space, empty space with a cosmological constant in it. And then our observable universe has an upper limit on its entropy. So the observable universe starts with a very small entropy and then increases, but only to a finite amount. That's kind of an important thing. That's a very different situation than what Dyson had considered. And I looked a little bit for, was there anyone talking about this important impact on Dyson's argument, but I couldn't find anyone. Probably it's out there somewhere. I'm probably not completely original in what I'm about to say. But the entropy of our observable universe has an upper bound, which we think is about 10 to the 122. The universe will expand and thermalize, equilibrate to that kind of state where there's a finite entropy around us. What that means is there is an upper limit on life. Because that thinking, Dyson was worried about energy, not about entropy. So he imagined thinking, more and more slowly, using up less and less energy. But computation, the kind of computation that is relevant to life and thinking, increases the entropy of the universe. Roughly speaking, every bit of information that is processed increases the entropy of the universe by 1, okay? Now, you can argue about this. There's details. There are reversible computations and things like that. But the fact is that the kind of computations that are relevant to thinking, remembering, predicting the future, stuff like that, do generate entropy. They increase the entropy of the universe around you. So if thinking, and therefore if living and thinking increase the entropy of the universe, and there's an upper limit to the entropy of the universe, then guess what? There's an upper limit on how much life there can be in the future history of our universe. So how much life can you fit into the rest of the universe? And here, this is just, my back of the envelope calculation. Again, someone probably did this more carefully, but here's what I came up with. If you ask about the total entropy production of a single human lifetime, you can actually look up the numbers. Human beings increase the entropy of the universe around them by about 10 to the 23 bits per second. I don't know where that number comes from. It's mostly the infrared radiation that we're giving off, okay? And that's safely above the number of computations that we're doing. The number of computations in a human brain is roughly 10 to the 20 bits per second. And I said that every computation increases the entropy by 1. So the fact that the computation rate is 10 to the 20 bits per second, the entropy production is 10 to the 23 bits per second, is perfectly consistent. It's just saying that most of our entropy production does not come from thinking, which is probably quite realistic, right? Like we're also just sweating and radiating out into the universe just by maintaining our temperature and things like that. So, okay, let's take the total entropy production of a human being and let's multiply it by a century, right, for the typical human lifetime. And let's get 10 to the 29 as the number of bits of entropy generated in a typical human lifetime. Call that a human life equivalent, 10 to the 29 bits per lifetime. History to date, if you just count the number of human beings who have existed, is about 10 to the 11 human life equivalents. Actually, actual human lives, as a matter of fact, in that case. But we're imagining that maybe in the future, it's not actual human lives. It's, in the Matrix or something like that, or some kind of collective intelligence. Who knows? We're just talking about the entropy production in a typical human lifespan now, projecting it into however that might be instantiated into the future. Well, if you have the Earth lasting for a long time before the sun expands, right? Like let's be down to earth here. Let's take the number of humans now, about 10 to the 10 humans on the Earth today, and let's imagine that we exist just here on Earth. We don't colonize the sky, okay? And we last until the sun blows up. Then that's about 10 to the 8th centuries, 10 to the 10 humans right now. So that's 10 to the 18. Human life equivalents. So in other words, we've had 10 to the 11 human life equivalents so far in history, another 10 to the 18 to go. So we're nowhere near everything that could be accomplished just here on Earth as long as we don't do something dumb like ruining the Earth while we're here on it. That's still nothing compared to what happens if we do colonize the stars. If we go out into the sky, fill the Milky Way galaxies, 10 to the 11 planets for the rest of the lifetime of the stars in our galaxy, we get up to 10 to the 34 human life equivalents. So this is how many human life equivalents could be experienced by life forms in our Milky Way galaxy between now and when the last star dies, 10 to the 15 years from now. 10 to the 34, way bigger than the 10 to the 11 that have actually existed here on Earth. And finally, just to, blow our minds a little bit, I said that there's an upper bound on the total amount of entropy we can fit in the universe, 10 to the 122. How many human life equivalents does that count as? Well, if it's 10 to the 29 bits per lifespan of a human being, that's 10 to the 93 human life equivalents that we can fit into the universe. That's a very, very large number, 10 to the 93. So if we did nothing but harness all of the resources in the observable universe and put them to the task of thinking, of acting like human beings, whatever that means, to think and learn and love and write poetry and whatever, you could do that for 10 to the 93 human life equivalents, which it's not realistic but that's the upper bound. We're not trying to be realistic and say that's what would happen. That is the maximum number you can contemplate. And 10 to the 93 human life equivalents is a very big number, but it is finite. That's the final lesson here. The final lesson here is, given that our universe is moving toward thermal equilibrium, that it is cooling off and getting smoother and getting eventually kind of bland and featureless and going toward a situation where life itself cannot exist. It doesn't matter how clever you are. It doesn't matter how you marshal the resources around you to sort of say, well, I'm going to build a bunker. I'm going to pack enough food to last longer than the universe, et cetera, et cetera. You can't do it unless you die, unless you literally don't exist. As long as you are still existing like a human being, still having thoughts, still increasing the entropy of the universe, there is an upper bound to doing that, okay? It's a bound that is very, very far away, completely irrelevant to our current existence here on Earth, but it is there. So the bad news from cosmology is immortality of human beings, or even of the human race, is not a foreseeable prospect. You can still live a long time, don't get me wrong, but true immortality is beyond our grasp. There's one little footnote here with which I will close this whole holiday reflection, holiday message, which is, okay, is it possible that the last loophole maybe is maybe we human beings will just equilibrate into the universe around us, but could the universe be immortal? Could it last forever? Yeah, that's absolutely possible. It's absolutely possible for the universe to last forever. The conventional picture is that we just, of course, expand from the Big Bang, from the hot, dense state. Our entropy increases toward the future, and eventually we hit de Sitter space, and then nothing ever happens. But nothing ever happens for an infinite amount of time. So that is absolutely a kind of immortality, right? But if you think about why the early universe had low entropy in the first place, that's a big mystery that we don't have a good answer to. As most listeners know, I wrote a paper back almost 20 years ago now with Jennifer Chen that proposed a large-scale model of the universe, large-scale cosmological scenario in which most of space and time is precisely local thermal equilibrium. De Sitter space, empty space, nothing there, nothing going on. But if we add to that the possibility that there can be a quantum fluctuation that creates a little baby universe in some local region of space, even if the rate at which such fluctuations happen is very, very, very small, you have infinity years to wait. So eventually you will get lots of baby universes, and they will, inside them, actually typically a baby universe will just recollapse right away, but if conditions are just right, it can expand and inflate and have its own arrow of time. It can expand and cool and have an initially low entropy just in the baby universe before it expands and thermal equilibrium eventually happens, and there's a temporary period where life can exist in that baby universe before it eventually goes back to its quiescent, empty state. And in this scenario, there will be an infinite number of those baby universes in which that happens. So I kind of like this scenario. I like it because it helps explain why the early universe had low entropy, but I like its implications for immortality. And this is, the happy conclusion I came to when I was thinking about what to say at the Santa Fe workshop. In this scenario, the universe lasts forever, but most of it is dead, right? Most of it is empty space, nothing going on. There are brief little fluctuations where complex systems, including living creatures, can come into existence in the baby universes and in their aftermaths. But there's a good news, bad news situation here. The good news is that that will happen forever. So there will always be future beings in our future light cone, in the future of our universe. There will be thought, there will be love, there will be caring and meaningfulness and purpose, at least temporarily, in regions of space and time that will exist in the future of our universe. That's the good news. The other news, which I'm not going to necessarily call good or bad, is that no information is passed from universe to universe. The process of the quantum fluctuation that makes the baby universe doesn't rely or depend or care about what came before. It is a completely, it's blind to what the conditions of the universe were that created it. So whatever universe is created, and again, our universe might very well be one of these universes that came about by this mechanism, it doesn't know what happened before. We can hypothesize about it. That's what we're doing right now. We can think about it. We can say the existence of a pre-existing universe is the best way of making sense of the universe we see, but we can't know. We can't talk to them. We can't communicate with them, nor can they communicate with us. So in some sense, this kind of cosmological scenario is the ultimate ceremony of forgetting. It is the ultimate way that the universe renews itself, rejuvenates itself, by forcing us not to stick around in a way that Ted Chiang would be happy about. We can't impose our thoughts and preferences and so forth on our far, far, far future life forms because they can't possibly know about us. We have forgotten. They have forgotten us. We have forgotten whoever came before us. And maybe this is the universe's way of saying that's how it should be. You shouldn't have the baggage of an infinite past, nor should you be able to put constraints on the infinite future. That's a good way for the universe to keep going forever while still maintaining some freshness about the whole situation. That's the holiday message for this year. I hope that you had a good 2023. Nothing's happening next week for Mindscape, so we'll see you in January. Have a great holiday. Take care.